and also he has published many books, and currently he is being one of the authors of the following books. And the PTA, Post Tensioning Association's Model Specification for the Design and Performance of Post-Tensioned Concrete Floors in Building Structures, first edition. And then Concrete Society Technical Report 43, Post-Tension Concrete Floors, third edition. And I Structural Engineering, then Concrete Society Standard Method of Detailing Structural Concrete, fourth edition. So these are some samples of his experiences, past experiences. And today we are going to have we are going to receive a very good lecture by Mr. Suren Nadarajah, and we are really happy to have him as for his IEI lecture. We are happy to welcome you, sir. Please.
Right, thank you. Good evening, everyone. But thank you for the long introduction, Dr. Manjula and Dr. Kumaresan. Thank you. So I hope this will last about an hour, right? It's going to be about an hour, right?
Yeah.
Okay, how is the questions? Is it along the presentation, anyone can ask the question, or we leave it at the end of the presentation?
At the end of the presentation, because they can put it in the chat box if they are intermediate, and we can do it at the end.
Okay, all right. Okay, this is, I really, when Dr. Bhaskar asked me about something, some presentation on it, I really thought this may be a useful for you all, because I have been in India many times and visited a few places, and even Delhi and all, few projects and all. So I felt it's something India industry may need to improve. Especially that should start from the engineers to the constructors to the architects and everyone, even the operational staff. It has to be started off. So I really thought, just to quickly cover, I assume this all of the audiences are engineers and they have this mainly the civil engineering background. So they should be able to understand what we are going to talk. So I just wanted to touch on briefly the techniques, what we are talking about, the pre-stressing, and also some background on the design, and followed by the construction. So then after this, I would like to put through a few of the projects as a kind of a case study, or you can call it as a project sample, so that you can have a look at it, how it's adapted onto it. The agenda for the today's one is, first I would like to put it on the techniques and applications, then a little bit of design concept already. I would like briefly touch, not really go into detail, and then types of pre-stressing. What are the benefits? We are going to mainly concentrate on post-tensioning, because that is the one used around the world. About 80% of the projects, more than 80% is used as post-tensioning. So that's the most, that's where we are going to concentrate on today. Then a little bit of a cost model study against the other available solutions, so where this post-tensioning stands. And then some of the construction aspects and the examples at the end of it, the Q&A with the conclusion. So the pre-stressing technology is actually, it's a simple mechanism which we normally do day-to-day activities, but we don't really realize that's what we are applying. When we are taking in library some of the books, we used to have press it, put it together and press it and carry. So this gives a compression, pre-compression to the book, so that it intacts next to each other, and then you are able to carry. Similarly, our standard, the cart wheels, if you look at it in our everywhere in our countries, even here, like a hose cart and everything, what they do is they have the timber ring, and then they have a slightly smaller diameter of steel ring, and then they heat up the steel ring and put it into the wood and then suddenly cool it. What happens is this compresses all the spikes and the wheel. Then it has more capacity to run it. It has a pre-compression. Similarly, this is the beer and wine barrel. Like in our places, like a drum, our merlam. If you look at it, that's always they use like a tighter bands, leather bands, and tighten up. This gives, again, this is simply called that pre-stressing. So that if you look at it by words, it's a pre-stressing is a kind of a reinforcing concrete, but it can be applied in different ways. What we are doing is we are giving an external forces against that applied forces. So what we are doing is exactly like what we have done on the three above. We are giving additional pre-stress. Then the post-tension in that pre-stressing can come with another extra factor, which is an eccentricity. So you will have some kind of additional moment as well we can give it. So if we look at where we are using these pre-stressing effect, if you look at it, nowadays this pre-stressing is used in many places, buildings, especially in the Europe, Western nations, all the tall buildings, mostly done by the pre-stressing technology. The reason is here the height of the buildings are restricted due to the airspace requirements. So there is a reason to reduce the slab thickness. So it is used, traditionally used in the bridges. It can be either internal or external. You can see it's a box girder inside. It's used in the tanks. In India, this is very, very popular in LNG tanks. Most of the LNG tanks are constructed using the post-tensioning pre-stressing technology, because when the water is coming, it's pushing outward the loads. So we try to bring it back. So this is very popular. And another way of doing it is the pre-stressed tanks. If you look at on this LNG tank, this is very, very tall. So the wall, thicker wall, you built it in concrete in an in situ manner, like about 3-4 meters at each cycle. It could be like a 20 meters, 30 meters tall with a diameter of 30 plus meters. But there are some other tanks, especially in the European nations, we need this for the vegetation, that we need to keep the water inside certain tanks because that for the farming during the winter times, we need to use it. And also the water treatment plants. Here we use our household water when it comes out. We can't really straight away put it to the sea. So what we do is we try to recycle it. We try to sanitize, and we get that into few tanks. That is not high. It is about less than 10 meters tall, but the diameter would be 50 meters, 60 meters. These are constructed normally with the precast panels. Each once you can see that one panel, then there will be holes, pre-installed ducts, and then strands will come in, then finally tighten up. Staircases, we do quite a lot, like a freestanding staircases. If you look at it, this is a spiral staircase, this is very recently we completed. Is all threads are precast. Then we put it together through the strands. You can see that strand is connecting all the way bottom to the top. So only support is top at the bottom, spiral nature, very thin, very slim, and it looks very nice. This is used at pre-stressing. Straight staircases, this is about 15-meter long staircase from one place to the other. So this is connected by the pre-stressing technology. Then you can use like a heavy lifting operation. So this is a lowering slab. We have done one of the job. It's a top-down construction. So on the ground level, from ground level with a plunge columns driven into the soil, then the superstructure carried over. But what we have done is on the ground level, we cast two slabs together on top of each other. Then the digging started, muck away is done, the excavation done. Then once the excavation is done and below is ready, we lower the slab into position. So it's a heavy lifting application. Another one is Omnia slabs, which we used it, say certain cases, your self-weight could be crucial. You may need to put more reinforcement just to counteract the self-weight impact. So for that, to reduce the self-weight, there are void formers used, which we call Omnia slabs, where you can use with the increase the compressibility tendons. Other places, bridge bearings, you can replace the bridge bearings by lifting off that one of the female section or male section and then replace the bearings. This is, you can use the propping. See at the bottom, you can see that the jacks are there. So when you have, this is the bridge construction. So we need to lift off the bridge and then provide the underneath the bearings, all pads need to be replaced. So you can apply this pre-stressing force into the temporary work structures. Tower crane ties, you can use these and the tower cranes or the basement. Here, if you are having a, say, 220-meter tall building, our tower cranes is a wind is an issue. So you need to tie like every about 5-6 levels, you need to tie with the slab. So that tying, we use that pre-stressing technology to hold it. Or we can have a torquing, sometimes we may not be able to stress it, but only by using the nuts, we just lock it actually, basically by providing torque. This is indirectly giving a pre-compression. Bar stressing, this is like recently we did one of the job. If you look at it, the core, when you build a large core, the foundation should have that minimum weight to hold that building to resist the wind. But at the time of construction, you may not have that weight. So the foundation may float into it. So to avoid that, what we do is we tie the bar from the foundation and then put an extra force onto it. Once your top structure is done, you remove that force. Flat jacking, you can use this in many places. Like if you want to replace a roof, like in a stadium or something, steel roof, if you want to replace it, you can just use this flat. This is a very slim jack, less than 50 millimeter or 100 millimeter max thick. You can raise it up and then remove that in a different way, and then you can replace. So flat jacking used. So in many circumstances, these are used. Now, if you look at on the principle, I just would like to quickly touch on the principle. When a structure is there, when the load is coming, tension is produced. This is the standard behavior. So when the tension is produced, at the bottom, the crack will happen. How we resist that when using reinforced concrete is we provide the reinforcement at the bottom so that the cracking can be controlled or deflection can be controlled. So the reinforced structure, that cracking is resisted by the tension. We are adding extra tension by the reinforcement. However, on the pre-stressing condition, what we are doing is we are applying a pre-compression so that the tension is the concrete tension or cracking or deflection is resisted by the pre-compression of the PT. So in broad, if you really look at it in a technical manner, both are different. Both are same, not really different in resisting the crack or not, but the way it resists is slightly different. One is in tension, one is in pre-compression. So what we are doing now by calling pre-stressing is at the mid-span where you normally get deflection or cracking at the bottom, we are pushing upwards so that we reduce the crack width or we reduce the deflection. So when you lift it off, you need to distribute that moment or load to somewhere. So what we are doing is we are bringing that load onto the column location and dumping the load onto the column. So by lifting natural behavior, it will deflect over here. So very minimum moment will be transferred onto the column. Whatever it can take, it will take it. But on the pre-stressing, we are lifting off this. By doing that, we are distributing the moment onto the supports and we are giving more loads onto the column. So this is exactly what we are doing. Now, if you look at it, I just wanted to have a look at this one. This is what exactly happening when the load is coming. This is what is happening. Now, if you look at what the pre-compression is, pre-stressing doing it, we are applying a force so that we are giving a reversible moment. So it's deflect upwards. Then the loads come in. It is coming like almost as a flat. So what we are doing is at the early stage, we try to balance certain load of the structure by applying a reversible moment onto the structure. Okay, so this is basically, we call it load balancing. Normally, this is what we do. We decide how much load we wanted to balance it. Say if it is a car park, normally you will have a very long spans. Like in here, if you look at it, 15.6 meters one direction and the other direction is 7.5 meters. So that you can park 6 cars, 3 cars on one with a driveway, and then another 3 cars you can park it. So that's a reason that grids are almost identical for all the car park. For that, you can really, the self-weight would be probably quite a substantial amount for the 15.6 meters. So we will balance the self-weight. Some cases, say if it is an office building, you always have your desks and books and certain things. So you will balance it more than the self-weight. Some load from the live load, you will balance it. So that's the amount of pre-compression is decided by how much balancing you wanted to do it. This diagram just gives you an idea. So basically, this is the purely on the technical term, the last diagram, it shows where that compression and tension is happening. So we are going to that on the top, there's a compression moment is induced, bottom a tension moment is induced. By providing the PT, pre-stressing, what we are giving is we are giving some pre-compression, as well as because of the eccentricity, we are giving some moment. So the resultant effect, what we are giving is this much. So if you compare this one against this one, we are we are totally taking away certain kind of tension from that. So this is the principle we are using. Now, if you look at it on the pre-stressing ones, there are certain things we need to consider while designing the flow layout. It could be many different layouts. This is some of the 3 layouts I have chosen, which we recently completed in London. The first one is called 150 Bishopsgate, which is a 5-star hotel, a Malaysian investment. It's in the central London. If you look at in these 3 corners, 6+ meter cantilever. No supports at all, but 6 meter cantilever. But the support, how we have done is, so 6 meter cantilevers, of course, it cannot be done. So we used vertical stress bars, 4 levels vertically, then we transfer back to the column, the nearest column we connected. So it's a complicated design, but it's a flow layout. It allows you to apply the PT central core for stability and all around the columns and the slab. Similarly, you can have equal spacing. These are very popular grids, popular layout, which will offer you optimized user space compared to the stability reason, the core. Sometimes you may need to have too many cores. So these kind of the things are one of the best layouts normally used. When we look at on the pre-compression, pre-stressing, one of the item in the design we need to consider is the restraint. When we say pre-stressing, which means we are applying a pre-compression, only that slab, particular element is effective when that pre-compression is transferred into the slab. If that is not transferred into the slab, then it is not going to be effective. Say, for example, we don't use that pre-stressing technology on top of a pile cap or something, because if you have a pile foundation, then with a mat slab on top of it, the piles are extremely stiff. When you apply the pre-compression force, it can't go into the middle of the slab. What will happen is it's concentrated where you are applying. So if there is any restraint, any stiff element is there, then you need to be very, very careful. So if you look at on the first diagram, it's all columns. When we apply the pre-compression on this slab, both sides a little bit shortened. The shortening in general, if you look at about like a residential or something, you can expect about 0.2 to 0.3 millimeters per meter. So which means if you have a 50 meter width building, you are talking about 10 to 15 millimeter shortening will happen totally. So each end may be about 5 to 7.5 millimeters shortened. By doing that only, the pre-compression is going in. Let's assume in this second diagram, we have a core at this side. So if you have only one side core, then one side slab can move. So if you have, this is the central core, it's very stiff, it can't go, but this slab can move downwards too. So this is still possible, but there are some layouts, it cannot be done. Say the first three are favorable because it's only one location we have the restraint. All other areas it can move in. If you look at this wall is in minor axis. On the major axis, of course, it can't move, but there's a minor axis, so it can move in. However, if you look at the last three layouts, which may not be favorable because these are too stiff. This area, if you look at it, this area of the slab, these two cores can't allow to move. So what will happen is if we put the PT here without a proper assessment or a provision, it may crack. Similarly, this layout between here and there, all that. So this restraint need to be carefully looked at. How we are overcoming this restraint is either you can produce a post strip so that this is an infill strip. You wouldn't cast this one at the time of construction of the slab. So this slab can, when you stress, it can move towards this stiff core, and this slab can move on. We can technically calculate based on the time distribution, like I would say is a load history type of way. So say 30 days, how much it will shorten, 60 days, how much is shortened, so that we can decide when do you want to lock this area. Or similarly, nowadays we use a lockable dowel, which is a shear dowel, but inside it's like a male-female connector. It can move freely until you lock, until you grout this area. So this will allow, we don't need any supports underneath. You can continue your construction. Whereas if you have a post strip, you need to have a table, you need to keep that support underneath. So there are ways to overcome this, this shortening. So it need to be taken into account while designing this one. One other thing is the robustness and progressive collapse. This is something very, very important. So sorry, I'm not much familiar with Indian standards, but I'm pretty sure it should be there the similar way. So it allows the slab to tie between the supports, so that a progressive collapse nature, unless you design as a key element, the slabs should be able to resist a certain amount of force. So which should allow the people to escape when a flow is failed. Before the lowest flows are totally failing, the people from the underneath, they should be able to escape it. So this is something, this is irrespective of whether you are doing post-tensioning or RC, this is something we need to do that. The reason I put this slide is I have been on to few of the big projects in India, but they never did a check for this. So I felt this is something probably Indian code deal with slightly differently, but our British standard or Euro code very explicitly, it gives you the guidance as how you need to do it. It gives us, the purpose is if you can see that before this phase, or most of the time, failures happens at the connection. You all know that you don't really see that failure happen because of just a cracking or something in the middle of this. But most of the time, it happens at the connection area where you are connecting with the columns or walls. So that's where we need to tie it. So there are processes given. You need to go for like an edge connection, horizontal tie, you need to go for it, peripheral ties and internal ties, you need to do it. So this is something, again, design need to be taken into account. I just parked that on the design part. Now, quickly, I move on to the type of pre-stressing. There are two types of pre-stressing. One is pre-tensioning, the other one is post-tensioning. By name itself, you can understand the first type is, it says you need to tension before you cast that concrete. So it is what happens. This is the precast factories. You will see that mainly like a bridge segments, precast bridge segments. They will have a strong stressing bed, and then there will be buttresses, and jack would be there. The strand would be stressed, and then concrete would be cast. Once you cut, you just cut on these two areas. Once you cut, that pre-compression, that strand to try to pull in together, so this element, this middle beam will hook up to take that load. It's at the end, it has to be in equilibrium, so applied load and the resisting load, so it will be getting hooked up. Hollow core slabs, I think in India they use a lot. The hollow core slab, exactly the same technology used, which is called pre-tensioning. On the post-tensioning, by name, what we do is you install all the tendons, we call it tendons or strands, and then cast the concrete. After you cast the concrete, then you tension it. So when you tension, this is where we will have the parabolic curvatures, or this is depend on we can provide the load, how much we need it. It is on site level, it would be applied. It's an in situ element. So it will have a strand, you will have a strand, then a grout, and then you can have a duct, or you may have just only a strand with a grease and the sheathing. So now you can see that pre-stressing has two, one pre-tensioning and post-tensioning. Again, the post-tensioning has two systems. One is called unbonded, the other one is called bonded. So unbonded means we don't really grout that tube inside. It's a strand, its a purpose is the pre-compression would be given at the two ends of the slab or beam or whatever the element. So it will have a tube with a grease inside, strand will be inside. So when you stress it, the anchor are at the end of two slabs. So middle, it can have parabolic nature or whatever required, but so based on that force, it will pulling up. Whereas the bonded tendon, which will the strands will be covered within a duct. You can see that four strands are there within a duct. You stress it, then once you have proved that stressing, then that void between the strands and the duct to be grouted. So this once grouted, that means the strands are bonded. So the significant difference between the two is, if you look at on a bonded tendon, since the strands are connected through the grout, duct, and the concrete, the load is transferred wherever it touches. The pre-compression is transferred wherever it touches. So if there's an accidental damage, it's very localized. It's not going to be able to pull through anything. Whereas unbonded, if you cut somewhere, because it didn't hold it anywhere in between the slab, it will fly through on the edge. So that's why when you look at an unbonded, at the two ends, there will be a cover. There's a safety cover would be there to avoid flying end. Then if you look at it bonded, we need a grouting, but unbonded not grout. And each one has different reasons to use it. Say unbonded is lower friction. So if you have a very less load, but if you want a larger span, then you may use unbonded, because it's like you can lay that unbonded one by one as a reinforcement. Whereas if you have a very heavily loaded area, you need to have concentrated load through ducts, so you will have a bonded. But in the UK, Europe, and even in Asia, 90% of the works are done based on the bonded. Whereas in the US, it's an unbonded is slightly low, more sides, about 30 to 40% they use unbonded, and 50 to 60% as the unbonded. One of the other difference you will see it on unbonded, that vibration resistance is much less. You can understand that's because it's not connected, not really monolithically connected. So you will have the vibration responses more. But it's at the end of the day, it's a perspective of the people. If you are standing on a car park, if it vibrates, in the UK, if it vibrates, that's a big thing. That's a big call will go out. But in the US, people don't care. That's fine. That's meant to be. So it's a perspective of this, but mostly bonded is the one used. So I try to concentrate on post-tensioning bonded is the most. Now, benefits of post-tensioning. Now you should have already got that idea what will it give. The first thing is the flow thickness. Normally, about 20 to 30% of the thickness you can reduce for an equivalent RC slab. So say if you have 300 thick RC slab, you could be able to do 240, 250 thick slab. You can easily do a PT. So especially when you have, say, here we do very often, I'll show some of the 167-story tower we did. Basically everywhere, 25 millimeters if you save it, which means you are providing one more floor extra to the client. That's a huge benefit and huge cost. Say one floor means it's a substantially beneficial and cost benefit onto it. Long spans, like if you have a lecture theaters, you don't want like a temples, you want the large areas. And if you look at our temples, exactly this is the kind of the solution that previously our kings has done it. If you look at, if you go in all the temples in Trichy, and it's amazing the technology what they have used at the time. So punching shear resistances, how they have done it, it's a fantastic. So you can create, but the same thing, nowadays we can't do that kind of the work. So we just try to use with the minimum concrete, minimum expenditures. That is where you use the post-tensioning and constructability quick, because very less reinforcement would be there. One PT, one strand, if you look at it, which is 1860 Newton per millimeter squared ultimate capacity strength, which is compared to a reinforcement 460 or 500. So you are having about 3.5 times higher, 3.5 times stronger than the rebar. So your amount of reinforcement on the deck is less, so that you can cast it quickly. And mostly you can do a flat slab. You can avoid beams underneath by designing the two-way slab with the post-tensioning, simpler formwork, and there are many benefits come to it onto it. How we design it, Euro Code 2 for us, it gives us the guidances. And one of the main document is this technical 43 report, and it would be very soon, it would be released, the 3rd edition, which incorporates a lot of the recent FIB and the Eurocode committee works. We have done many of the revised based on the experiences, and we try to put that on. So this document, the TR43, is one of the probably easier, simpler document to understand, design, and get it everything. I think this is straight away will give you a very good information. Then quickly a comparison. You can have normally structures, you can have a flat slab, all the underneath is same, or you can have a band beam and slab, or you can have a rib slabs. Ribs actually basically like a one-way beams with the smaller beams, thickened area than the slab. Waffle slab is like a two-way type of process. So these are the 4 normally applied in everywhere. And the beam ones, if you have a deep beam, you just normally call it beam slab system. So it's a somewhat similar. So this is the 4 categorized one. If you look at the most benefit is coming from actually the flat slab. It's a construction is easier, formwork is easier, everything is much easier. Reinforced, normally you can go up to 8.5 meters with a reasonable 9 meters, reasonable thickness. Whereas that same thickness, you can go up to about 12 plus meters. So that pre-stressing allows you to go larger column free space. Same thing on the beam, same thing on the beam, you can do that. And if you look at it, see the waffle slab, one of the interesting thing is, the reinforced slab, straight away it's go to 9 plus meters. We don't use anything for waffle slab, anything lower than that. But pre-stressing, you can use it. You can thin down the element and you can use it. So there is a significant benefit you can do by the PT, converting that RC into the PT. On the program ones, normally here in the UK, if it's an RC, we normally go about 7-day cycle. But by doing post-tensioning, we can save 2 days, so 5 days a cycle. Say if we have a 60-story tower, if we turn around the cycle 7 days to 5 days, which means we are saving 120 days, which is a phenomenal benefit here in the UK. The earliest you sell the property, you get that money back and interest, and also that's a huge saving. So the program is substantially saved. So you can easily say 15% of the program, you can save it easily, but there are chances you can do even 20% or 20+%. Then I just quickly touch on the cost model study. This will give you an idea is how that PT to be post-tensioning to be applied or pre-stressing. When we say pre-stressing, there are benefits, but it doesn't mean you can apply everywhere. You have to really analyze where this gives you the most benefit. You simply should not say anything can be done on the post-tension. There should be a proper analysis needed to be done. Say commercial property, we have taken, and this is the Concrete Society, taken and study, and they have published as a document on a typical commercial property where the shops and all there, a hospital building, which is a ward, not the operating theaters, because that's a very particular areas, or that is scanners are there, which are very heavily loaded. And there's normally schools and also. So when we do that, you can see that the three options used. One is the RC flat slab. The other one is a post-tension flat slab. Then the other one is a composite section, steel with the concrete. So if you look at on a school, the most beneficial is the PT flat slab. But composite slab is better than the traditional RC slab in school. The reason when we say school, you know that we need to have a corridor for the children to run away, and they have to have a classroom which normally occupy 30 to 40 kids. So there is a minimum spacing is there. So what's happening is there's a large end span with a small span at the corridor. And then when you look at it along the building, you will have that repeats everywhere. So that scenario, that condition is almost similar. You don't have a shear wall or core. So that all should be resisted by the brace, by the columns actually. So when you have columns, that's why you can't go too tall of the school building. Generally, you will have maximum 2 floors. So that's why that RC structure is expensive compared to the other. Whereas hospital, tall buildings, you will have shear walls, you will have a particular arrangement for the number of wards. And normally what will happen is you will have a long corridor type of the room. Bed is there, but you don't, one direction you have large space, but other direction you will have columns. But that may be a multiple areas you can have it. So it's a slightly different. In this case, the composite slab is expensive because the governing criteria would be the longest offside area. In an office, it is purely a cost. We are talking on the cost. It's very interesting if you look at it. Office building, normally you go 3.5 to 4 kPa loading, maybe 8 to 9 meter grids, you will go for it. RC flat slab is competitive to the PT flat slab. Of course, the composite is very expensive, but PT flat slab. However, the difference is that PT flat slab has another benefit. One is thin slab. Second one is the large room you can have free of the column spaces. So there is other benefit. This is purely on the cost wise. This is a kind of, and give you an idea, which shows you PT post-tensioning doesn't mean that's good always, is better. That's the reason for this slide. One of the hot topic, carbon study now. If you look at it, almost all similar range. So basically, once we started off using concrete and the steel, very difficult to go away from it. This is why now a lot of researchers try to do. I remember Dr. Bhaskar also, they did some kind of different thin wall structures they did on their PhDs and all. So they try to look for different composite material to get this carbon body to reduce. Once you get it, not much of a difference. To be honest, there is not much of a difference on the carbon. So as long as we do a concrete structure or a steel building, very, very difficult to control the carbon. So now in the UK, what we are now very often, nowadays very popular is we use the GGBS, the replacement mix. Instead of cement, we use the chemical waste as a supplementary product for the concrete cement. So we used about up to 40–50%. Very often nowadays it's used. So this is something like, we are having quite often, but still carbon is one of the serious problems, especially when it comes another 20 years. We need to rethink what's the best way to do it. So researchers are trying to avoid reuse the concrete or reuse the steel. They try to get that benefit of this. This is on the first part done. Now, quickly, I would like to move on to the construction side. So then after this, I will have a project one. I think we are probably on time. So there are 4 stages we need to look at it. One is installation, stressing, grouting, and then a sequence. It is a process-driven approach, so I just wanted to go onto it. On the installation, you need to follow certain sequencing. This is, as I mentioned, this is a process-driven or driven solution. So you need to really follow this. You cannot do a duct before the tube or after the tube or anything. You can't do this operation before you completing one of the lowest operations. So it's very, very, very much it's a process driven. That's why this is called a specialist industry, like steel structure, pre-stressing, specialist, because that has a process driven approach. First thing, on a table, you need to make sure that you have the deck is safely erected, and especially the areas where the column, say when you have a circular column, you may have to have a special formwork underneath. So need to be very careful before the people get onto the deck. Just need to make sure the formwork is done properly. For the stressing purposes, you need a space to stress at the end. So you need to have a deck for about 1 meter. Then the first operation, once the deck is ready on a post-tensioning operation, is similar to reinforcement. What you normally do is deck is ready, you bring the reinforcement based on the drawing and install it. Similarly here, we need to install that tendons or strands. The strands will come in a coil, it's about 3.5 tons. So need to be given appropriate safety measures. Lift it off to the deck. If you can see that we are using the lifting using the rope, not really by the chain. So you should not lift these things by chain, because if you do, then you will damage that strands at the corners. You go into a dispenser, it will be safely tied down all the strands. Then once you go into the dispenser, you will remove it. And now because of 3.5 tons, where you are going to keep it on the deck, it has to be carefully thought through. So the location of that 3.5 tons, where we are keeping on a formwork, is very crucial. You need to find, say this is the closer to the column locations, this is again closer to these columns, and then underneath the formwork, you need to be, strengthen that area to take that 3.5 tons load. So this is need to be careful. Then on the next stage would be after strands is done, you need to use the components. I believe in India, you don't have a requirement to use an IOTA, European Technical Assessment Body's approved product is not necessary. But in the Europe, UK, we must use one of the ETA approved products. This goes to a rigorous testing. One of the important testing is 2 million cycles of vibration. Basically a cyclic testing, it's tested. So it's connected to the jack, and 2 million cycles when the slab is moved. That means people are coming and going out, deflecting and not deflecting. 2 million cycles should withstand. So here we need to use those components approved by them. The first operation on site after landing the deck and the anchors, what they do is they need to fit that anchor onto the deck, onto the edge shutter. They mark the tendon first where it should go, then drill it, and then they connect that anchor into it. Now, this is a normal formwork. You can see that a wooden formwork, you will connect it. And now here we use a kind of, we call it metal edge shutter, which we reuse it. So this I'll touch when we are going down. You can see that the cladding connection channels are pre-installed. Then after installing that anchors, you will install the duct, you connect the duct and make sure that no leak is going into it. So that then you cut it where you want it at the appropriate size. Then the next stage would be you need to install these strands. That strands can be installed by using a mechanical means. There's a small device so that it's pulled in. If it's a long tendon, you can drive through a machine. On the other side, someone needs to be there, and he has to make sure that enough length is come out. He needs to say stop. This is all very, communication should be very, very important. If not, it may be shoot out longer than needed. Other option is manual inserting. Manually, you can install where you have a small length, like a 10 meters or something. You can, machine is very difficult. It's quickly it's come out 10 meters. The acceleration is more. So you will use a manual methodology to install. Once done, once we install the strand, at the end of the day, we are going to apply a force. So one side we are applying a force, other side we are going to cast into the concrete. But when you cut, because the amount of force what we are applying varies from say 180 to 220 kilonewton, which means 18 to 22 tons. If you look at it in a layman term, like a 20 numbers of BMW 7 Series cars, the weight of the 20 numbers of BMW cars. So that if you stack up, that's the amount of weight we are applying onto each strand. So if you don't anchor this dead end sufficiently into the concrete, when you apply the force, the strand may come out, is pull out. But if you want to do that, if you want to take that bond stress of the concrete to the steel, then you may end up, you need 3 to 4 meter long strands to be installed, to be connected by the concrete. If you do, you are basically 3 to 4 meters in effective zone. So to avoid that, what we do is there's a bulb is created at the back. This will take about 60% of the load, 60 to 70% of the stressing load just by this bulb. So the remaining about 700 to 1 meter is enough so that this is, we can live with it. That's the reason if you can see that you have the reinforcement to cover that area. So this is the bulb and dead end they make it. Then once they're done, they will install the live end. This is the live end where we are going to stress it. This is anchor. There's a pocket so that we can cover it. So at the end of the operation, you don't see anything outside duct. And this is the dead end. Now, when you apply the force, a concentrated force is applied at the surface. So to avoid bursting effect, we need to have a closed links. Is a spiral link we provided so that the force applied force, concentrated force, can be distributed within the concrete so that no failure has happened. So this is very important to install this one. Then once you have done that anchor duct and the dead end bulb, then you need to provide the chairs to get the profile. Based on the design, you can have a parabolic, different parabolic curvature, depend on your moment. So we are providing the tendon force directly opposite to the bending moment. So you need to adjust the tendon to the required height based on the drawings or design. You can use a plastic chair or you can use a metallic chair. Either way you can use it so that you can connect it. Once you've done that, then we need to, at the end of our stressing operation, we need to grout it. So we need to have that grout tube connected. And this is a sticky tape, gaffer tape, we call it, a denso tape, which will really will not allow any water or slurry from concrete or concrete mold is going into it so that the duct can be free of space. Then, the same thing, we will go into the live end. You will see the tube. So live end and dead end, you will have the tube. So when you grout from one side to the other, the grout will flow through and it will fill in. These are some of the photos once completed. Say if you can see that this is about 1,000 square meter area already installed tendons. There's a bottom mesh we will have. Early days, about 10 years before, until about 10 years before, we don't provide a bottom mesh. The pre-compression by the tendon is more than enough. But Euro code come up and it suggested for the anti-crack and fire reasons, we need to accommodate few of the methodologies. So one of the easiest option to accommodate is the providing a bottom mesh. So in the UK, if you look at it, almost all the slab, you will have a minimum of 6 millimeter or 8 to 5 to mesh at the bottom. Then this is one of the one. See here, you can see that this is another area. This is a good photo. The two columns, you are having a heavy reinforcement on top of the column for the punching shear resistance with the shear studs. And the tower crane is going through the slab. So we have accommodated this slab with the tower crane opening, which is about, if you can really see, that is quite a big 1.5 to about 1.8 by 1.8 meter. So we will install that couple of bars all around. Then once the tower crane is down, then it will be connected and cast back. So then this is you can see that the parafolic tendon profiles very clearly on this deck. So this is another one. If you can see that this area is totally open. The reason is this is designed as a soft spot. When we say soft spot, initially all would be cast as a concrete. This would be cast as slab. Then when an owner needs it, he can make this as an opening. The provision is provided. That's why you can see that there is a reinforcement at the perimeter, just creating an opening. It could be for a purpose of a staircase can come in. If this is actually a shopping center, this particular is a shopping center. So there's a possibility 2 floors, 2 units, a same retailer can buy it. If he buys it, he would say, I won't have that staircase or the additional elevator to in. So we accommodate this one. So this is designed as the first case is designed as an RC slab for the design load. Second case would be designed as an opening with an additional load on the perimeter. Third case would be designed as you cast it back. So there will be a couple of bars as well installed for the future casting. So this is called soft spot. This is the punching shear studs. Here in the UK, we use studs rather than shear links. Shear links, you need to have hooks on the top and the bottom to develop the tension on the links. Otherwise, the links can't work. You need to have sufficient hook. But that's a very time-consuming installation, really, really time-consuming. So we use stud, which is on top and bottom, the headed bar. That headed bar creates that holding force, and then the tension is created at the middle. You can see the straight. So this much actually on site would be installed in 15 minutes, 1 column. Whereas if you do a shear links for this particular case, it will take about 3 hours to install by 1 person. So this time saving is really, offset the cost of the shear stud. Shear stud is expensive, but the time saving is very, very beneficial. Then, we accommodate the precast column. So if you can see that the precast column is with a space at the middle for the slab to cast. And here you can see that we have the punching shear studs and the reinforcement is going through. So here, normally you will have column to slab bars will come in. But here we design like a pin supported rather than a certain fixity we take it. But still you can transfer some moment. That's why we leave this hole. We can transfer the reinforcement through here like a hidden beam type of thing, so that you still can transfer some moment. So this is very common nowadays in the UK. And I just quickly show you a video, the installation video. This is the realistic side nature. Bursting link. They are cutting the duct. So if you look at it, the ducts are laid over there. Bursting links is there. Some of the ducts already installed with the strands. This is a top mesh. So this is how the installation will go onto it. Then now that once the installation is completed, next stage would be stressing. Once you cast, next stage you just clear off the pocket, and this is how you will see it. Then you connect the block and the wedges. This is the conical shape wedge, which will allow you to, once you pull in and then you release it, it will lock in. Because we need to make sure that our theoretical force is transferred on site. So for the designer, he needs to know whether the force is applied onto the site, onto the strand. So what we normally do is the measure is, we know theoretically how much the strand need to come out while you put the 220 kilonewton. So what they do is they paint it, and then once they stress, it will come out, and they measure that distance and tell it to the designer, and he will check against his theoretical value. If that is within a range of plus or minus 6% or 5%, he would say yes, he would be satisfied. His design force is already applied in the structure, so that structure can take that load. So this is how it will look like after you stress the tendons. This is the extensions. Then once you do, you cut it into it just to make sure you will have the sufficient cover to make sure that no water ingress or the fire is not affected. So you will cut at least 25 millimeter cover, you leave it and cut it, then use the sand cement paste to wrap it up. So once done, this operation, stressing operation is completed. Once the stressing operation is completed, you can say you can remove the formwork, you can totally go out. However, you may need to cast on the top level. So when you cast on the top level, load would be going onto this deck. So you need to back prop it. So this back propping design normally done by the temporary works designer. All these jacking operations, there should be a calibration need to be done. And normally in the UK, we recalibrate every 6 months. So one calibration is only valid for 6 months, so that you know you are not missing any parts or anything, any little bit loose like oil leak or anything, you are not going to have it. If you just quickly, I'll show a stressing video. This is the one guard, that's a jack. You can see that they continue to do that, and then they just release that stressing. So this is the stressing operation is done. Once done, then we will move. We have to, because the bonded tendon, so grouting need to be done. Before do the grouting, the supervisor will go and check everywhere that tubes are damaged or anything. If it is damaged, he will repair that with a connector. Then they will send a high pressured air from one vent to the other vent, so that any trapped water or debris can come out. You can see that all come out, so that they knew that it's a clear of any debris. Then the grouting would be prepared in a grout pump. In the UK, we use a pre-backed grout, which is like all the additives added in the factory, and they will come up with 20 kgs bags, and we just need to add 10 of them into a 70-liter water and 4 minutes mix it and then pump it. That's all that we do. But I think in India you have cement, then additives and all separate, because there are chances you may miss that amount, miss that one, so you may end up that grout may not set at all. Grouting is very, very important. If your water content is more, then the grout never set any time. Because of the additive nature, the property of the additive, it may never set. So that's a very dangerous situation. So we need to make sure that grouting is an important one. There are some tests need to be done. This is to allow to understand that grout is suitable to grout it. There are some parameters need to comply. And this is what I said, that 10 of these bags, they will add it up and then they mix it. So once they mix it, then first they will do a test. It's called sieve test. This sieve, the intention of this sieve test is there any solid particles or not? When they pour it, there shouldn't be any solid particle remaining on the sieve. This sieve is Eurocode certified one. The square mesh is a particular size. and it is defined as a 0.5 millimeter square. And then this is the safe test to ensure no debris or no solid particles. The other one is fluidity test. This allows the fluid nature of the grout. It can easily flow through, but it will set. So normally it's about 12 to 20 seconds. So normally we get about 15 seconds. Then there is another check we do, like this is a wick test, we call it. This one is how much bleed that material between the strand, how much it's taken. But it's not really a relevant product for us, because when you do this, you only measure that bleed 2 days later, but at the time the grout is already there, so may not be relevant to it. Then this is how the grouting operation will happen. From one end, it will be stated, and the other end, the guy would be waiting to see that. When you pressurize grout, he will see it's come out. So normally about 4 to 5 liters, we don't use it. We just waste it because it may be water and all will come up. So about 4 to 5 liters once come, he will close that tap and leave it. So then next day when he come and he can have a look at it on this, the grout is already done. And on this, at the end of this, that entire pre-stressing operation is completed. Just briefly, a quick video. This is the grouting pump. He's putting the time and they are mixing. Testing they're doing. Equipment they are setting up on site. Yeah, this is they do. Then if you look at it, this is another video of the grouting operation. You can see that. They will ensure that same tendon they are grouting. You can see that it's pumping by the pressure. Yeah, you will keep some pressure even after closed, just to ensure it's pressured and everywhere it's filled in. Okay, so now that's a full operation is finished on the grouting, that's all done. Then one of the aspects is we need to see always when we build a structure, you need to consider demolition as well. So post-tenure pre-stressed concrete is not much different to the RC. So this is a test is done. You can see that how it's not really much of a difference between RC or PT. See that ducts are hanging, and so demolition is not really significantly different compared to RC or PT. So now, just quickly wrap up that procedure so far. What we have done is installation sequence. There will be a formwork erected. Then you will install the bottom reinforcement and H rebars and any trimmer bars for the penetration at the bottom. Then tendons, we would install it. And then after installing the tendons, there will be a top reinforcement installed on top of it, including the punching shear studs and any cladding channels or anything is required. And then after that, you will do the inspection and concrete. So this is a highly process-driven sequence to be followed. And this is what we do on an operation. After doing this, for the purpose of future maintenance, operation and maintenance, we need to submit an operation and maintenance manual, which it is a document which will consist of everything in it. All the drawings, all the site records, including the pre-pour inspection, concreting space, pegs, grout strength, concrete strength, and certificates for the strands, which strand coil, which batch number goes into the which deck, all that records we will keep it. Particular coil, if we go to tendon number 1 to 5, level 1 for 1, it would be recorded. And all the plant and materials, what kind, which jack we have used, which type of jack, which calibration certificates, and every day you have the toolbox talks and method statements. Everything would be put it up, and we call this an operational and maintenance manual, and which would be kept. So this is the final completion of the design and operation. So we designed the post-tensioning structure, then we ensure that design principle is transferred into the operation, into the site. Now, quickly, I would like to put through some projects. I think is that time is okay. Another 5 or 10 minutes should be okay, right? Prof. Maresan, is it okay?
Yeah, maybe 5 minutes, sir.
Yeah. Okay. So just quickly, if you look at it, it's a BBC plot A. This is the World Service one. We built it. It's a 10-story. You can see the 9-meter grades, and you can see that this is at the bottom. You can see that for the punching shear, the column capital is there. This is the tendon layout. You can see that steel transfer columns are there, dead ends. Column capital, this is a column we designed with a certain stiffness ratio, certain fixity, so the column bars are coming in. This is the lockable dowels and concreted. This is the Imperial, this is an Imperial College. There is an accommodation, which is a 35-story tower in a slightly different shape. So this is the tendon layout if you look at a typical floor. This is how it's constructed. This is a wall. If you look at it, the load is shear wall. It's in an angle. We transfer the load from here to there. This is the screen, which is edge protection. This is again connected. It will jump every 2 levels. So it's similar to the core jumping. You can really, it's similar to that. So it's a very, very useful. This is the hoist where you can move the stuff up and down. So you can see this is another view how it's cast, the concrete and the PET. And then if you can see that the core, this is the stressing end strand is come out. Again, we use the precast columns, double height columns. And one of the reinforcement nowadays, what we do is the reinforcement, we prefabricate. So we, like a mesh, we detail this one, and the manufacturer weld all the bars and bring it like in this piece. So we just drop it. So we don't really on site fixing this rebar, like a bottom mesh. This is we use. And this is again, as I said, this is the edge shutter, which we'll use for the repeatable usage. So we try to maintain the tendon locations, holes would be there. And this is the edge shutter connection. See, you can see that the metallic edge shutter. This is how it looks like. This is the Newfoundland, the 60-story tower. Is one of the very prime locations in a banking district, Canary Wharf. You can see that this is the steel frame external and the central core. The stability is central core and external frame both together. This is on top of 2 underground tunnel, railway tunnels. So we have that plates welded into it. This is the model if you look at it, how we designed it, tendon layout. And see, you can see that how we have constructed this one. See, every 4th level we cast first, then the PT floors are inserted into it. You can see that because of the mega frame, we need to cast that, otherwise the stability is not there. You can see that this is the tendon layout. See, this is another view of it. See, this is where we use that the robustness reinforcement passing through the steel column, and this plate is providing the support for the punching shear. You can see this is the tower crane ties, and this is the completed project as it is now. This is another 61-story tower, which is called Wood Wharf. This is again a circular building. You can see that this cantilever, all this designed by post tension so that the cantilevers can be supported. See, this kind of cantilever area, the temporary works is quite important. We need to design quite correctly, otherwise it may deflect the lowest floor. So it need to be designed very carefully. See, this is the completed project. This is the complete 61-story tower. This is all residential tower. This is another, this is the South Cape Plaza one. This is again our project we already completed. This is 67-story tower. This is 61, this is 67. And then Heathrow East car park. This is probably a hybrid solution we used with the precast elements with an in situ and post tensioning. So this is the model we have done, analyzed originally. So this is all precast. This is precast. The shell beam we used it. If you can see that this is the shell beams we connected, then service holes preformed, anchors connected to that edge slab, column unit. This is a mock-up we did to see that how that the concrete behaves while stressing. That's a column. This is the one unit shell beam is lowered. Shell beam, installed all the shell beams. Then this is the edge beam, and this is the precast slab, solid slab. Then edge one, you can see that the angle, this is a preformed, then we connected the ducts onto it. This is how it will look like. At the end of it is like this. This is the car park. The completed project is like this. If you can see that this is a very, very high quality. So next time when you're coming to Heathrow in London, you can go to the T2 Terminal 2 and you can see this massive, the beautiful structure. This is like a jigsaw puzzle. It's like each pieces we connected into it. And now come to the conclusion. I'll just briefly touch on. As we looked at, pre-stressing has many benefits, and we can do a lot of impossible things to make as possible, like a long span beams. We can do that, like many methods on top of the tunnels. We can cross it, bridges, and many things we can do by pre-stressing. And its applications are varying from buildings to bridges to tanks, special purposes, and everywhere we can do it. It is very, very important. It's a process-oriented method, actually. So we need to follow that. Then we use that. It's really advisable to use that the IOTA approved components, which will ensure the safety of the product. At the end of the day, a collective approach is required to be success of this one. That collective approach should be start from the engineers to architects to constructors to the operational staff. Everyone need to be on board. Then only it can be delivered well. And that's all my little presentation. Hopefully you should have hopefully you would get some knowledge about it, and I'm happy to answer any questions if you have.
Thank you. It's a really excellent presentation.
Oh, thank you very much.
I'm an electrical engineer, but still I could follow something on this. That presentation is very nice.
It's really good.
So it's available in the YouTube permanently. So I think that the person working in this area, they can view and understand the recent trends in this.
Okay, all right.
Yeah, Dharmalingam sir, you have any clarification?
Good evening, sir. I am Dharmalingam.
Yeah, good evening. Yeah.
Okay, you have made an excellent presentation.
Thank you.
I find a lot of advantages with respect to the post-tensioning technique.
Yeah.
Can it be adopted for the construction of apartments with the 4 floors?
Yes, we are doing a lot in the apartments, but if you're having 4 floors, I'm not sure. It's based on whether you will get the maximum benefit or not. Because if it is a 4 floors, you are bringing another trade, another business, another constructor into your business. So you may need to, administer them, and you need to work with them, and you may have some kind of the, premium you may need to pay initially, because that plant and all, the initial cost is there. So if they come up for like a 10 floors, that initial cost wouldn't be significant. But if you have a 4 floors, they try to cover that cost on your 4 floors. But still you can use it. Depends how much you are going to the area you are having, but yeah, it's still applicable. Yes, definitely still applicable. And the grids, if you have like an 8 or 9 meter grids, then that's really, really good. Otherwise, it may not be. If it is a 6 meter plus 6, 7, may not be beneficial.
Beneficial, okay. Another aspect I find here is we have to maintain a lot of documentation, it seems.
We do, because because the problem is in future, we don't know anyone wants to do any additional works like a coring or removal or anything. So we normally have at least 24 types of documents we keep it ourselves. That's we pass on to the client and the constructors so that they can, in case in future they wanted to do like a coring or anything or fixing, additional fixing, they can use that to identify that.
Okay. Thank you, sir. Thank you.
Process driven, we need that.
Okay. Thank you very much, sir.
Thank you. Thank you.
So, thank you, sir. Any other clarification?
Suren, I am Bhaskar speaking.
Yes, Bhaskar.
Yeah, I have 2 questions for you.
Yeah.
Okay, in seismic, vulnerable area. So yours is mostly flat slab sort of thing. But when it is subjected to lateral load, there will be, the reversible stresses.
Yes.
How will you do the pre-stressing?
Okay, what we do is, to be honest, Bhaskar, there are not much of the literature available for how we need to design on a seismic area, because currently all the is a seismic, but the fundamental difference is the connection, how the load is transferred through these supporting elements. So the connection rebar is substantial, even though the diaphragm action is there. So for the older literature, even that FIB, our documentation, everything we are having related to the reinforcement. However, post-tensioning actually provides a much more resistance to that seismic. A couple of years back in Dubai, there was a building fail. Dubai is all designed under the seismic nature. So what we do is, for that particular case, the tendons next to the support, we will provide within a certain distance, normally within 0.5 D of the slab, of the beam or slab, we will have one tendon, all 4 sides. So that will provide, that will create a grillage around the column. So within 0.5 D, one tendon will go through it. So there's not many literatures, but actually it improves the seismic resistivity by providing the post-tensioning. There are researches done, they are proved, but none of that come into as a code of practice or as a guidance from FIB. We normally use that internationally, we use either FIB guidances or the Euro code. So both is still not put it together, that documentation, but obviously it is industry-wide accepted. If we keep the tendon within that 0.5 D, all 4 sides of the column, it enhances the seismic resistivity.
Okay, thank you. I mean, the next question, simple for you to reply. Basically, how, when we have a floor system, how will you decide the spacing between the tendons?
Okay, so
in some places it is closer to each other, in some places
yes, there is a recommendation. I think the TR43 gives you proper guidance. We do not exceed anything more than 10 times of the effective depth of the slab. So the between the 2 tendons should be limited to 10 times of the effective depth of the slab.
You mean the maximum spacing is 10 times?
Yes, that's right. That's right.
Okay.
Maximum, say if you have 250 thick slab, you shouldn't go beyond 2.250. About say, assume 25 millimeters is your cover. So effective depth is say 225. So you 2 tendons shouldn't be exceeded. If you are exceeding, you need to provide the justification basket. The justification would be point load. Say if you have a office building, each usage you have to check either UDL load, like a 5 kPa for office or 2.5 kPa residence. Similarly, you need to do a point load check. So if it is a car park, we need to check 9 kilonewton point load should be able to withstand anywhere in the slab. So what we need to do is, if you exceed that 10 times, you assume that two tendon, like I say in a 250 slab, you have 3 meter centers. That 3 meter has a simply supported span, and put that 9 kilonewton at the middle of the slab and see whether that concrete can take it or not. If can't, you have to provide additional reinforcement in between the two tendons to transfer that 9 kilonewton load. So generally, if you call it within the 10 times, if you keep it, you can easily call it, it's a pre-stress slab or post-tension slab. But if it is exceeded, we normally call it partial post-tension and partially reinforced slab, because you need to provide reinforcement onto it.
I see. Is there any codal provision for that spacing 10 times the?
Yes. I'll send it to you separately, Bhaskar.
Oh, fine. Thank you very much, Suren.
We'll do that.
Yeah.
I have written something on guidance. I'll send it to you separately, Bhaskar.
Okay, thank you.
Thank you. Dr. Bhaskar, maybe in a minute or two, will you be able to consolidate the lecture, today lecture?
Oh, yeah. Okay, you are, okay. Fine, I'll do that. Suren,
Yes.
it's an excellent presentation.
Thank you.
Everyone is, they are chatting in the chat box, everyone is appreciating your presentation. To be frank, in India, engineers are very familiar with the bridge girders.
Yes.
Okay, PSC bridge girders, maybe like I sections or rectangular sections, and even box, trapezoidal box and everything, but not in building side.
Correct.
Okay. But now it is coming up, in a large number. So many people are coming. VSL is also, established in India. And, the Eversenda is doing that kind of construction here. Okay, slowly things are improving here. And many buildings are coming up with post-tensioning slabs. Okay, in that scenario, I'm sure many engineers are not exposed to this building, at least I can say. So your lecture will, throw some light on this particular subject. Definitely, every engineer will appreciate, and they might have learned something from your lecture. It is very, very interesting. One thing is, you are presented in a very highly professional manner, like more than a professor. That I should appreciate really.
That's correct.
Okay. And you starting from application, principles, cost model analysis, even carbon study. Okay, then the construction aspect. It's a construction aspect really very impressive. Okay, from the starting point to the ending point. I never expected this kind of very clear presentation. And I don't know this is it your is it marketing presentation? I don't know. But it contains all the technical matters, okay, including the how to filter the grout. Okay, the grout should not have any dust particles or whatever. Each and every minute aspect is discussed here. This is very, very interesting, very impressive, very useful for the participants here. Definitely, they will appreciate. Apart from all, I wondered, when you are presenting the demolition aspect. I never thought about it. Okay, how to demolish the post-tensioned building. It's really great, really amazing presentation. On behalf of IEA and on behalf of all the participants, I really thank you very much for the presentation. And you keep going in this, and I came to know that you have written some textbook also. I think definitely, it will be useful for the civil engineering community. Thank you very much, Suren, for, I know you are very busy. You are the partner of that company and also technical director. I know very well you are so busy in the busy schedule also. I made the request and you accepted it, and you made it. Okay. So thank you very much for everything, Suren. Thank you very much.
Thank you, Bob. It's a lot. And to be honest, if it is really useful for some people, I'm very glad that that's what we really wanted, we wanted to disseminate our knowledge to the next generation. And I never kept anything within myself. Always we try to do ourselves to give others all the important points so that the industry as a collectively can get that better. And especially, I'm really glad I did this for the Indian industry, because always, whenever a building collapses in India, it hurts me a lot. It hurts me a lot. It's a people's lives, no one is bothering, how to, it's a simple design once, even the foundation, they do like in a simple soil, they just do a 1 meter or 2 meter footing and the building collapses 5 stories and they construct without the permission. So honestly, if this has helped to some engineers, at least 1 or 2 engineers got something useful, I'm really glad that. And thank you for this opportunity. To be honest, I have done, normally I do through many presentations to the Eurocode and FIB internationally for the industries, but never thought of, doing in India or no one is, but it's something, when you do it for your home country, you always feel something different. The feeling is different when you do for somewhere else. I always think, our knowledge, we give it to someone else, not to our people, but I'm really glad that's why my team, our detailing and design team is in India, in Trichy. They are the one doing if you look at most of this project for ones, is all detailed in Trichy. The Karthikeyan, skyscraper, he is the one did that. He was, I know him for many years while he was in Bangalore. So I'm really glad if that has helped everybody. And thank you, Bhaskar, for introducing me to you.
Thank you, Mr. Suren. So before going the formal vote of thanks, next week, the IEI Tiruchirappalli arranged the lecture on artificial intelligence and the robotics, transforming academia to industry. Speaker, Dr. Munish Jindal, founder and CEO, Power Robotics, mentor of change, Niti Aayog, Government of India, founding president, MentorX. So same will be, available in dailies, today's column also. We'll send the invitation to all our fellow engineers. Now may I request Engineer Samidas to propose vote of thanks.
Sorry, before go on, sorry, Prof, is it, am I able to view that your next week presentation on that?
Yeah, sure. We'll send it.
Oh, thank you. It will be quite a bit of an interesting topic. Yeah, thank you.
So we'll add your email ID and all the lecture. We'll send it to you.
Okay, thank you very much.
Yeah. Before go to that, I also wanted to add one more thing. Suren, actually, Professor Kumaresan asked me to organize few more from civil engineering at a regular interval. I contacted Tamarai. He agreed to give underground construction. Tamarai Kannan.
Oh, okay.
Okay, and one more from Venkat on environmental side, and
okay,
few more.
Right. Venkat is in US right now.
Yeah, he is in US. Okay, so I'm planning to get them into this forum, and they're ready already. They're ready to do that.
Good.
And one more point I just wanted to add, sir. For all others, Suren was actually doing computational mechanics side in his research. Okay, we never thought he will be in the industrial side. Okay, when he was doing his masters, it is totally on computational mechanics. But now it is design and construction. It is really amazing. Thank you, Suren.
Thank you.
So Tamarai Kannan, once the program is finalized, I will send you that link also.
Yeah.
Professor Kumaresan will send you the link.
Yeah. We'll by default we'll add his mail ID.
Okay.
Okay,
sir.
So, Samidas sir, you can unmute.
Yeah. First of all, I would like to thank Mr. Suren Nadarajah. Actually, I am a mechanical engineer. I never thought that I will sit glued to your presentation for such a long time. But it was a very good presentation. I would like to thank you on behalf of all the participants and members of Institution of Engineers, Tiruchirappalli Local Center and Tamil Nadu State Center. It's a wonderful presentation. I'm one of the past chairman of Trichy Local Center, age at 75, but still at this age, I enjoyed the presentation. Thank you very much on all our behalf. I also would like to thank all the participants for joining this today's lecture. Have a nice day. Thank you very much. Thank you, Dr. Kumaresan. Over to you.
Thank you, sir. Thank you, Mr. Suren, for your wonderful lecture, and we'll send you the link for the every week lecture.
Thank you very much. Thank you, everyone.
Thank you. Take care.
Thank you.
Sir Ramadas, sir, we